1, 2, 3, 4. Oh, wait, hold on. Let me check to see if it's streaming. 1, 2, 3, 4. All right, let me hold on. 1, 2, 3, 4. Live stream should be online. Hold on. Hold on. Hold on. Oh, not that one. Oh, jeez. Oh, jeez. Oh, yeah, we're up. We are up. Okay. Hello, everybody. This is actually, I think, the last operational section that we're going to be covering in this particular chapter. After this, we'll do some applications, some word problems. It should be pretty fun. Okay, so this lesson is on breaking up rationals. We're going to use something called the method of partial fractions, which is a pretty long-winded name, method of partial fractions. But it's actually a lovely technique that involves some logic and that involves some algebra. I really like it. It shows up in the Math 101 course at a slightly more difficult level. And so it's an appropriate time right now to talk our way through it. We introduce a lot of math techniques in this method of partial fractions. So by the end of this, you will be able to hopefully recognize when partial fractions can be used. So it's like the what's it called? The Heimlich maneuver. You only use the Heimlich maneuver sometimes. So when can you use the Heimlich maneuver? Essentially, you'll be able to recognize when we're allowed to use the partial fractions maneuver. After it, you'll be able to split a rational with a factored denominator into two monomial rationals. Like I mentioned before, we're gonna focus on a fairly easy version of this, but it gets the point across and it's pretty fun. So you'll be able to split one rational whose denominator is factored into two pieces. And the last bit, you'll be able to solve a pair of linear equations with two unknowns. This should be a review from some high school, but it's probably been a little while, so we'll review how to do that. Okay, let's begin. Okay, last lesson we talked about combining two rationals together. So somebody gives us two rationals like this, and you add them, and you get 10x minus 4 is equal to 2x, x minus 1. Hold on, that equal sign. Like I said before, and I've been focusing on this over the course of these lessons, some people get caught up on these equal signs. Are we saying that we need to solve this expression? No. What this equal sign means, it's not an equation to be solved. What this equal sign means in this context is that we started out with this expression, and then we rewrote it like this. And so these two expressions are equivalent, right? And so, in other words, what I'm saying is you start out with this expression, and then you do a lot of math, and then this is your destination expression. They're the same expression, I've just rewritten them. That's what the equal sign means in this context. You don't actually have to solve anything. So like I said before, you start on one side, and you end up on the other. So one question you can ask is it possible to go the other way? Is it possible to start with this one and break it into two pieces? And the answer is yes. You can't do it all the time, but when you can, we can figure out what these two terms are using something called the method of partial fractions. The name itself is derived from partial fractions. So for instance, if you go, let's see, 2 over 3 plus 3 over 4. Okay, so if somebody gives you 17 over 12, this is from maybe elementary school, you can rewrite this expression 17. You can factor the 12 into a 4. Oh, geez. 4 times 3. And then you can rewrite this expression as some term over 4 plus some other term over 3. And the method of by partial fractions, we usually mean, in this context, you're breaking this up into two fractions, each one of which is a part of the whole. And I don't know, maybe you learned in elementary school that you can write this as 3 over 4 and 2 over 3. Don't worry about this whole fraction business. It's not actually relevant, but that's where the name comes from. Essentially, breaking one fraction number into two. We're doing it with rational expressions. Okay, so I mentioned as we started that it's kind of like the Heimlich maneuver. It's not something you can use all the time. So when can you use it? Well, the Heimlich maneuver can only be really used when somebody's choking, and I think there's another condition on it, and also if they're an adult. There's sometimes conditions. You can only use it in such and such a condition. With partial fractions, you only use it in the following situations. There's two things that need to be satisfied. So the first thing is you need a factored denominator. This is something you can do yourself. So somebody might give you a rational and then ask you to factor it and then break it up into partial fractions. I'm not sure if I will in this particular course because I want to test individual skills. And if you get the factoring wrong, everything else is not going to work quite right. But long story short, is the denominator factored? Remember when we were talking about factoring that there are some polynomials that you can't factor, you can't write in a factored form. And so those ones, if you can't write it in a factored form, there's no possibility of breaking it up into partial fractions. However, many you can. And so on any exam, I will give you the factored form of the denominator. So if you see the factored form, that's an important first clue. We're going to use the factored form to break it into pieces. Okay, so that's one part of it. The denominator needs to be factored. Okay, so check. And two, we need to compare the degrees of the numerator. Okay? You need the degree of the numerator to be smaller than the degree of the denominator. In other words, you can't, we don't do it on expressions that are, what's it called? Hold on. What's that name? Oh my gosh, I can't believe I forgot. It's such an important name. Improper. You can't use it on improper rationals. So it cannot be improper. Incidentally, that isn't to say that you're not actually able to do it for non-improper. We just only use, there's a recipe essentially, and the recipe only works on improper expressions. If it's not improper, you have to do something more clever. Okay, so here's the overall idea though. So this particular expression, the degree of the top is 1 and the degree of the denominator is 2, so it satisfies both these conditions, so I can break it up into rational partial fractions. Okay. So what do I want my final answer to look like? I want my final answer to look like there's a term that's x plus 1 only, and then another term that's x plus 3 only. In other words, I want to break it into two terms that are added together, where the first term only has this simple part of the denominator, and the second part only has this simple term of the denominator. And then the exercise, in this case, is figuring out what kind of expression goes in the numerator. Okay? So, let's begin. Now, one question you might ask is, why can't we do this for improper expressions? And the answer is that if we know that the expression is not improper, if we know that the degree of the numerator is smaller than the degree of the denominator, then we can tell you that the degree of each of these expressions will both be, I guess, proper. The degree of each of these the degree of the denominator is going to be bigger than the degree of the numerator for each of these. This is like children, right? This one has some attributes, and it has two kids, and the kids both have the same attribute, which is that the numerator has a lower degree than the denominator. Okay? Just that one property. It inherited it, like having black hair. Okay? So, so in this case, what's the degree of the numerator and what's the degree of the denominator? I'm just recopying right here. Well, the degree of the denominators are both 1, right? And so the degree of the numerators must be both degree 0. What does a 0-degree polynomial look like? It looks like a constant. So that's some number, and that's some other number. And I don't know what a and b are, but I know they're constants. X plus 1, x plus 3. I'll review all of this in a second, and I'll give you an overview on the recipe. But this is essentially what you do. You break up, you rewrite this expression in terms of two expressions that are added together where each of these has a simplified denominator, and then you write the letters A and B in the top. And the reason for this has to do with the degrees. Essentially, the degree of the numerator in your original statement is less than the degree of the denominator, and so that's going to be true for both of its children. And now the exercise becomes, what are the values of A and B? So how do we figure out that? Well, as far as we're concerned, A and B can be any number. I don't care what their values are. The only thing I care about, though, is that when I add these two together, you get back this expression. Let me write that out. A and B must have the particular values where if I combine the rationals, expressions, I would get back the original expression. Okay. So how do we do that? I'm gonna copy everything we just wrote down. 2x minus 1 over x plus 1, x plus 3 is equal to a over x plus 1 plus b over x plus 3. To reiterate, I want to figure out what the values of a and b are so that when I combine these two expressions, you get back that expression. That's the overall idea, because I want the rational to be the same. Okay, so how do I figure them out? Well, essentially, I already know how to expand or combine two rational expressions, so I'm going to do that. I'm going to multiply this one top and bottom by the denominator on the other one. And then I'm going to multiply this one top and bottom by its sister's denominator. Okay. And now I multiply everything out. So this becomes ax plus 3a over x plus 1 times x plus 3 plus bx plus b and I'm a little bit running out of space, so I'm going to combine them all in one step. So then you get a, actually, you know what? I'm not going to do that. I'm going to be brave. I don't mind that I'm running out of space. Maybe I'll move stuff up here. Make it closer together. All right. So then this becomes ax plus bx plus 3a plus b all over x plus 1, x plus 3. Which you can rewrite as a plus b all times x plus 3a plus b. Good, and I have just enough space. So the idea here is I want this to be equal to minus 2x minus 1 over x plus 1, x plus 3. Okay? Now for the fun part. This is an intermediate step. It's an important first step. I guess this is the second step. The first step is to write the expression like this. The second step is to combine them algebraically until you get this. Now the third step is I need to figure out what a and b are. Do I have any clues to their values? It turns out I do. So what I'm going to do here is I'm going to compare their values. I don't know what a and I don't know what b are, but I do know that a plus b, when I add their two values together, I need this coefficient to be 2. Okay? And I don't know what a and b are, but I do know that when I combine their values in this way, I get minus 1. Okay? So what you're going to do is you're going to compare these coefficients and write them out one at a time. I'm going to use a blue pen because we've entered a different stage of our calculation. So this is minus 2 is equal to a plus b, and minus 1 is equal to 3a plus b. And now I want to solve these equations. Solve the pair of equations. Now, there's actually a whole load of different techniques that a person can use to solve equations. I'm gonna give them labels. I'm gonna call this one 1 and this one 2, so that you understand what I'm doing. Okay? So this is just to help me narrate. You don't need to do this. So there's a bunch of different ways for solving equations in this. In other words, figuring out the value of a and the value of b, where if you plug them into this, it's satisfied. If you learned one in high school that you really like and you're good at it, I don't care if you use that. But in this course, I'm going to teach you a technique called it's called substitution. And it works like this. You're going to start by taking one of the equations. You just have to choose one. I'll choose I. Okay? And I'm going to rearrange it so that A has been isolated. So I can do that by subtracting from B on both sides, and you get A is equal to minus 2 minus B. Okay? So whatever the value of B is, if I knew what B's value was, I could use this equation, to figure out what the value of A is. Okay? So A has to have that value, and it depends on B, and so I can substitute this in for the expression with A in this equation. Replace A in equation 2 with this expression. Okay? Watch me do it. Minus 1 is equal to 3 times minus 2 minus B plus B. And now I expand. Get rid of those parentheses. Minus 1 is equal to minus 6 minus 3B plus B. and I simplify. So minus 1 is equal to minus 6 minus 2b, and then I solve for b. So I'm going to start by adding 6 to both sides. So it becomes minus 1 plus 6 minus 6 minus 2b, and you get 5 is equal to minus 2b. Wait, hold on. Hold your horses. Hold on. Oh, geez. Okay. So I'm just compared to my notes here. I was supposed to get a whole number. I just compared to my notes. When I started doing this question, I made a mistake. Instead of writing 10 here, I wrote 1. Okay? So I've been solving for a different equation than the one in my notes. It doesn't really affect anything. I'll just continue solving for this one. So then you finish it. So you divide both sides by minus 2. So it's minus 5 over 2. So I know b's value is going to be minus 2.5 because I plugged it into a calculator. Okay. Now I can take this value and I can use it to figure out the value of a. I substitute back in my original equation. To figure out the value of a. A is going to be minus 2 minus 2.5, so it's 0.5. Okay. So what does this mean? It means that I've figured out the value of a and b which are supposed to go into my original expression. So it was a over x minus 1, plus 1, right? Hold on. X plus 1, x plus 3. I'm sorry. B over x plus 3. I'm going to substitute these values back into my original expression, 0.5 for x plus 1 plus minus 2.5 over x plus 3. And that should give me I've successfully broken up my original rational into two parts. Okay, and let's confirm that this is right. So I'll multiply this through. So this becomes 0.5 times x plus 3 plus minus 2.5 times x plus 1 divided by x plus 1 times x plus 3. Nope. And this one's divided by x plus 1 times x plus 3. So this is 0.5x plus 1.5 minus 2.5x minus 2.5. And then you simplify this one more step, and you get minus 2x minus 1. Let's confirm that that's what I'm supposed to get. Minus 2x minus 1. Hooray, I did it right. Okay, so there are lots of intermediate steps to this. And so I'm going to show you a few different examples. We'll try another couple examples, but first I'm going to give you an explanation overview of how the procedure goes. Okay, so in partial fractions, you start out with a polynomial that looks like this. a rational expression that looks like this. Okay? Where 1, the degree of the numerator is smaller than the degree of the denominator. 2. You want the denominator to be factored as it is. So it's written in terms of two polynomials that are multiplied together. So step 1, write out the shape of the expression you want. Okay. So you want to break your original expression into two pieces that are added together. Okay? And the idea being that when you do, the numerators are all going to be slower degree than the denominators. So all of the ones I'm going to give you will have denominators that are linear. And so this expression will look like this: a plus b. A and b are unknown constants. Then 2, combine the two rationals added together. You know how to add rational expressions. You treat a and b like constants, and you just get r times x plus b times r of x divided by no, not b. Now, this thing I'm writing right now, it looks pretty weird. This is just a placeholder for an idea, which is okay. So don't get too caught up in it. This isn't a recipe I want you to use. I don't want you to start with this expression and then just copy that out. I want you to go through the intermediate steps of combining them. And then 3, compare the new denominator which is this one, to the original one. This will give you a set of equations right? So they'll look like, a plus b is equal to 4. And 2a minus 3b is equal to 17. I don't know. So you'll just get a set of equations like that. Step 4, solve the equations. Using substitution method. Or any other method for solving linear equations, and this will give you the value of a, and it will give you the value of b. And then step 5, plug these numbers back into here. Replace the a and the b with it, and then you're done. Okay. So let's try a few examples. The more examples you see and the more examples you try, the more obvious all of this will be. But regardless, I really like this method as for the start of this particular term because it puts together a lot of basic computations and procedures with a little bit of logic and a little bit of problem solving. So let's try this one. This is the original one that I wrote down up at the top, and I completely miswrote it when I started solving it. So let's try this one. Okay, so step one says I want to break it up into... Okay, so first I need to check the numerator and the denominator. What's the degree of the numerator? Here, I need a different color pen. What's the degree of this numerator? It's 1. What's the degree of the denominator? Well, this one's degree 1, and this one's degree 1, and they're multiplied together, so the total degree is going to be 2. Okay? So yeah, I can... And the denominator's factored here, so yes, I can definitely use partial fractions. Congratulations. So what's the final answer going to look like? It's going to look like x plus 1, some constant, plus another constant, x plus 3. And now I want to figure out what these two values are. So I'm going to multiply this one by the denominator of the other one. Make sure to do it top and bottom. You don't want to make any mistakes here. Okay, now I'm going to multiply everything out. Plus bx plus b, all divided by and so this becomes a plus bx plus b plus 3a. And now I'm going to compare this one to that one. And so the equation has to be, maybe for the sake of the screen, I'm going to write over here. I'll just fill up this space. So a plus b have to add together to be the coefficient minus 2. And now I compare these two, this one and this one. And so it's b plus 3a has to equal minus 10. So now I'm now going to choose one of the two expressions and then solve for isolate one of the variables. Yeah, for your sake, I'll call this 1 and 2. So let's do it for 2 now. So I'm going to take 2 and I'll isolate for b. b is equal to minus 10 minus 3a. And now I'm going to substitute it into a. A plus the b term is minus 10 minus 3a. 2. So that's equation 1 with a replacement. And now I simplify, and this becomes minus 2a minus 10 is equal to minus 2. So minus 2a is equal to, I'll add 10 to both sides, plus 8. And now I'll divide both sides by minus 2. Minus 4. So then you take this value and you plug it back into this expression, the one you solved for b originally. So it goes b must equal to minus 10 minus 3 times minus 4. So that's minus 10 plus 12, that's plus 2. So b has the value plus 2. So you take these two and you plug them back into here. So the result is, so a has the value minus 4 and b has the value plus 2. And now I can test it. Test. So this becomes minus 4 times x plus 3. It's always really helpful to test on this stage because it's really easy to make a really simple mistake on this. There's lots of steps. So if you test it, you'll get a little bit more practice in, and you'll also see if you've been doing things correctly. So this becomes minus 4x minus 12 plus 2x plus 2 all over x plus 1 times x plus 3, which becomes minus 2x minus 10, which is what I started out with. All right. Let's try another example. All right, so how about this one? 18 over x plus 4, 1 minus 2x. That one's a little bit more exotic. Okay, so just remember, we're going to start asking ourselves, can we use partial fractions? The denominator has been factored, so that's good. The degree of the denominator is 1 plus 1, that's 2. The degree of the numerator is 0, so yes, we can use partial fractions. So what do I want this to look like? That's step 1. There's a term that has a bottom x plus 4, and a term that has a bottom 1 minus 2x. And both of these have some constant. And now I multiply the first one by the denominator of the second one so that they match. I need to combine them. And I multiply this one by the denominator of the other one. So it's 1 minus 2x, x plus 4. And the result is a minus 2ax plus bx plus 4x. And now I combine them, so it becomes b minus 2a times x. There's an intermediate line I'm skipping here because I personally want to write this all on one screen. You can have a lot of paper to do this, so it's wait, hold on. Look at this mistake I made. I made a mistake right here. That's supposed to be 4b. One of the benefits of doing a lot of practice is that it becomes easier to spot the mistakes you've made. So now I'm going to compare. This one has to equal okay. So this one has to equal 18. A plus 4b has to add together to be 18. What about this term here? There's no term here with an x in it. Which brings us kind of back to the original lesson of this particular chapter, where I asked you, hey, what's the coefficient of a term that isn't there? The coefficient is 0. And so b minus 2a have to add together to give it 0. And now I'm going to solve them. Here, I'll letter them just so you know what I'm doing. I'm going to rearrange 2 solving for b. And then I'll substitute this expression in the first one. A plus 4 is 2a is equal to 18. So a plus 8a is equal to 18. So 9a is equal to 18. So a is equal to 2. And then plug that back into here. B must equal 4. So I take these two numbers and I plug them back in to the original. And so a has to be 2. And b has to be equal 4. And let's just test it. Testing is such good practice for you at this point in the game. I really encourage you to learn to do it. To make a habit of it, rather. If If you haven't noticed, it's really easy to make a mistake. I'm always making mistakes on these. So, yeah, a little practice will help you recognize when you're making a mistake, and will also make it a little bit less likely. X plus 4. So this gives you, these two cancel out, and you get 0x plus 18. And you don't write the 0x term. Hey, look, it's exactly what we wanted. Click, click. Okay, so that's all there is to partial fractions. So yeah, it's a procedure that I want you to learn how to use. You don't get much use of it. We'll get a little bit of use out of it a little bit later in the term when we start talking about graphing. But overall, its power, the reason we teach it now is because it really gets used a lot in Math 101. So please learn how to do it. It's fun, and it's good practice, and I'll talk to you later.